It proposed a new perspective for solving the Sandwich-Virasoro conditions in the context of string theory. The Virasoro conditions require that for all physical states, the contraction of two physical states and the Virasoro generators should vanish for all n. This requirement is usually solved via the right action constraint for all n greater than or equal to 0. Our motivation for this study is to show that there are solutions to the Sandwich-Virasoro conditions that do not necessarily satisfy the right action constraint. We categorize our different classes of states according to their behavior under this combination J0 and P0, and we find that we have 4 classes of states. For class 1, we essentially have the right action satisfied. Class 2 and 3 are those for which P0, respectively, and J0 behave non-trivially, and they take the physical states to the non-physical complement Hilbert space. And for class 4 states, both these P0 and J0 operators take the physical state to the complement Hilbert space. And in order to study these specific classes, we consider eigenstates of these J0, P0 operators, and we can write our generic solutions in these classes as a sum of these terms with alternating signs of eigenvalues that appear here, and S1 and S2 are 2 signs, and we have 4 choices for S1 and S2. And this specific choice is useful because we see that the action of P0 necessarily changes the sign of S2 and J0 the sign of S1, and we can write our different classes of states as a sum of these specific choices that we had for the physical states according to whether lambda plus or minus are 0 or non-zero. And in this context of quantized string theory, 0 plus and 0 minus have a specific form in terms of the left and right levels and the center of mass momenta, and we can write lambda plus and lambda minus in terms of these norms. We see that class 1 states are usual level matched tensile string theory states, and class 2 states have lambda minus not equal to 0. They can be written as a sum of 2 terms with left and right levels interchange, and we have this Mathieu condition for these states. Class 3 states have lambda plus not equal to 0, and they can be written as a sum of 2 terms which are separately level matched and a Mathieu condition. And class 4 states are more general. And we here show that when we have horizons on the worldsheet, these different classes of states naturally arise. We can relate the 4 quadrants of the Penrose diagram for the Minkowski space, left and right, Rinder and top and down Milne, via these mappings for tau and sigma. And we can show that the combinations JMN and PMN respectively preserve parity and time reversal. And we know that, as we have seen, J0 and P0 were the combinations that we used to categorize our different classes of states, and class 1 states are invariant under both parity and time reversal, and they are what a Minkowski observer who respects these symmetries will observe. Class 2 states break time reversal, and they are related to what a Milne observer will observe, and class 3 states break parity, and they are related to a Rinder observer. In class 4 states break both of these symmetries. And here we see this specific behavior in this schematic. As a conclusion, while 2D Rindler and Minkowski symmetries are locally the same of a wide factor, they can be distinguished according to their behavior under this Z2 cross Z2 symmetry. And while these 2 classes of states are not level matched or unshared in the usual string theory terminology, they can naturally arise when we have horizons on the worldsheet. And horizons on the worldsheet are important when we want to study strings probing black hole horizons. Thank you.